Recording started.
Good afternoon, everyone. Let us proceed on our next journey here with the output control on the microcontroller. And so we talked last time about the general characteristics of pulse width modulated signals. And just to refresh your memory, let me change my view here. We saw that we have these modules called the output compare modules. And basically what we're doing is we're generating pulse width modulated signals where we vary the duty cycle. The duty cycle is basically the percentage of time that the signal is high to, so I can calculate the time that it is high and divide it by the period of the signal and basically come up with the duty cycle. And we express duty cycles in percentage. And so for a normal square wave, our duty cycle would be 50%. But we'll find that this being able to vary duty cycles is very useful, so we can actually do some control sorts of activities. And so we'll actually see those. I have a hardware lash-up set up that I hope to show you, and so let's proceed. So what we do is we're going to vary this duty cycle, and we're going to use an input signal, and a convenient input signal that we have is the analog to digital converter. So we'll use that to provide varying levels to control how the percentage of the duty cycle. We'll vary it from some value by varying this pulse width. And the way the output control works, and I'm going to show you some actual examples of this here shortly, but let's talk about how we control it, and we'll look at the software configuration before we actually do some of the demos. So we will also generate tones, and I mentioned last time a square wave is the sum of a fundamental and the odd harmonics. And so if we have a low pass device or low pass filter, we can basically extract a sine wave from this square wave. Now notice in this case, I want to emphasize, in this case we're using the duty cycle of 50%. Now you may be wondering, well, how do we use our output compare to do this? Well, we can use the output compare by basically setting our compare register to 50% of the total count, and we'll get a 50% duty cycle. So let's look at refresh our memories how this works. We're going to use a timer. The timer will count from 0 to the value that's in the preset or period register, at which point it will reset. And this sawtooth behavior happens continuously as long as the timer is enabled. And so we're going to take advantage of this. We're going to use a timer to generate some reference, and our output compare is basically going to compare the value that's in the timer register with the value that's in the compare register. And if it is less than that value, depending on the setting we have, of course, then we're going to generate a pulse width modulated square wave. And so, or pulse width modulated wave. And so what we're going to do is we're going to vary this value so that we can vary the pulse width. And that fundamentally is how we actually operate the output control. So the way it works is we have to select a timer. The timer is going to provide a count, and we have very specific timers. And this timer, the timers that we can use as inputs are timers 2 and or 3. So I can use timer 2 or timer 3, or timer 2 and timer 3 for 32-bit count. And so we will write values into the compare register. Actually, we'll write them into the secondary register, at which point they'll be transferred into the primary compare register at the appropriate time and then used in the comparison operation. We have some options as to the type of output we can generate, and we'll look at those here very shortly. And so what we have to configure is we have to write values to the compare register and configure the output logic. And so let us look at the actual output compare module. So first thing we're going to do is, of course, always go to the microcontroller data sheet. And we see that, all right, same block diagram that I showed you before, and here are the SFRs that we have. So let's just look at output compare number 1. We see that we have 3 SFRs. We have a configuration register, we have the compare register, and then we have the compare secondary register. So these two have basically the same function. Again, we always update by writing to the secondary compare register, And so we'll configure these, and so let's just look at what the configuration options we have. As we have to do with every single module in the system, is we have to first off turn the system on. So this is the on function. We will enable or disable the system in the idle mode, so we can stop in idle mode or leave it running. We can indicate whether or not we're going to use a 32-bit compare, and if we use a 32-bit compare, then there's no questioning what the timers are going to be, because it's going to be timers 2 and 3. Or if I want to use a 16-bit timer, then I leave this bit at the value 0. I also have some status, so there is a, well, this octal select, this is selecting timer 2 or 3 if we are in the 16-bit mode. And the most important one for this is now, how are we going to configure the output? So we're going to use the pulse width modulated mode, and so here on either 7 or 6 will be our modes, and if we're going to use the fault pin, we can enable it or we can disable it. And so our value or the selection we're going to make is pulse width mode on output compare, fault pin disabled. So very straightforward kind of configuration. So if we look at some example code before we actually look at a demo, what we're going to do is we're going to use our analog to digital converter to provide our level. So we have our same clock initialization. We initialize our A to D, very similar to what we've done previously. We initialize our ADC. We're going to read it, and we're going to have a delay. We need a delay function in there as well. So basically, we just initialize the timer. We configure the timer because we're going to use the internal clock. So this is our delay init. This is our timer configuration. So we have two timers. One is timer for delay, and then timer 2 is for our output compare. Then we open our output compare, and we see that we turn it on, 16-bit, timer 2 is the source, and we do the pulse width modulation with the output pin disabled. And we're going to set it to some value, at this case 200, which is, so this is going to set the period of, or the width of the pulse width modulated signal for the initial setting. And we initialize.
I have a question.
Sure.
So on your open OC there, OC2, I see you're using OR symbols there. Or is this actually a logical operation, or is this just the syntactic setup for that particular function?
So what this is doing is this is setting bit number. Well, come over here. So when I say on, it's basically putting a bit in bit position number 15. When I do the next option, which is going to be the 16-bit mode, so it's basically setting ones or zeros in those initial bit positions and ORing them all together. So it's basically a 16-bit value with one individual bit set. And so as I OR all of these together, the bits that I intend to be 1 will all be set at 1, the others will be set at 0. Because if I set 0 ORed with 1, the result is going to be 1. So if any of these have a bit set and I OR them all together, then I set the individual bits as desired. And notice what I have here is I have my compare register and my secondary compare register set at 400. And so what I did is I set my output compare to 200. So now that I'm going to actually set it to a 50% duty cycle, and then I go into a loop. And what I'm doing here is I'm using my analog to digital converter. Recall that basically is going to return a binary value. from 0 to 1024. And so when I set that, I use that value, that's going to be my value that I write to the output compare register. And so what I'm doing is I'm varying the pulse width. So let me change gears. I'm going to kill the lights for a moment. And let's go over here. And let's look at it on the scope. Okay, so you can see the oscilloscope, and I'm going to go to the different camera. He says. So let me get a little closer here. There's an LED on this breadboard. So we get a little closer. And you can see, hopefully, the brightness of the LED, which might be kind of dim. Okay, so notice as I'm increasing the pulse width, it's still a little too far away to, it is getting brighter and brighter. And maybe if I had something black behind there. Okay. You still can't see it very well. At least, are you able to make this video larger on your screens? Anyone? Okay, so can you see the LED that's getting brighter and brighter? Okay, so what I'm doing is and unfortunately the human eye is very, very good at detecting light. And so as I make this very, very dim, you'll see that, and let's see if I can get any closer. So it still seems kind of bright. And let's see, I can maybe get a little closer. Okay. I can make sure I don't drop this thing. So there it is. We see our duty cycle is very, very small. So the average DC voltage, and in fact, there it's basically off. And as I increase that, you see it starts getting brighter and brighter. So what I'm doing is I'm basically increasing my average DC voltage across this LED, causing it to get brighter and brighter. And as you see the oscilloscope, you can also see that I'm basically changing the width. So I can, by varying this, change my duty cycle of my square wave. And we see that the period of this is going to be about 27 milliseconds. And that's governed by my timer setting. So when I set my timer, if I come back to the right view graph, so by setting the value in the timer, basically I'm going to shorten the period of this square wave. Okay, so I can also use that trick for my own, to my own advantage. So what I'm going to do is I'm going to run another demo. So let me stop this guy, start another project. And I need to do a little configuration of the hardware. Okay. And so now this one, what I'm going to do is I'm going to first show you what I'm doing in the code. Okay, so when I go to my code here, I'm going to use my same function, but I'm going to use this function called sound. And what sound is doing is it's basically going to change my output compare period. So I'm changing the period. I give it a frequency. I calculate what is the appropriate period for that, and I set my output compare so that it's at a duty cycle of 50%, and I'm going to vary the frequency. So, let's see, did I build it? No, I didn't build it. Okay. So now you should be able to hear. So what I should do is set up an amplifier to amplify that. But what I'm doing is, can you hear the changing scale? So we see how we're using the square wave and taking advantage of the low frequency response of this little buzzer to generate our tone. Okay, so you're probably wondering, well, why do you care about pulse width modulated signals? Okay, well, there are devices that we use that are very, very handy for things like robotics and other sorts of things. And those are motors like these kinds of motors, servo motors. And so what a servo motor is, a motor that basically has a limited range of motion. So imagine now I have a motor that's controlling steering on my robot. I need to move only in a certain range, maybe from 60 degrees from the left to straight forward to 60 degrees to the right. Well, that's where these kinds of motors are used. So they have a limited range of motion. So you see we have in this case, we have some sort of linkage that we'll put on top of the armature. We also have internal gears there that give us a little bit more torque for our signal. And so what we want is we want some way to be able to move this. Now let's see. So these kinds of virtually all motors are going to be open loop in that we know where we can move the motor from some relative position when we first start up. But as we talk about it, and we'll talk about it a little bit more on Tuesday, when we first, now these motors that we have here are actually, we know where the armature is positioned. We can control that. But when we have a motor that has just a pure rotational aspect to it, it basically has no idea where it is when you first turn it on. And so, for example, if any of you have a printer, particularly an inkjet printer, what happens when you first turn it on? What happens when you first turn on your inkjet printer? Anybody have an inkjet printer and they want to volunteer what happens when you power it up? Okay, so Nate has it nailed. It finds its home position. So when you have motors, particularly rotational motors, you hear lots of movement because what it has to do is it has to find a known position, has to find a datum. And so you'll find that on your inkjet printer, it moves the carriage back to a known position, its datum, its reference point, and then from there it knows precisely where it is relative to that datum. And so when we start using other kinds of motors, we're going to need to initialize it to know where am I. Okay, so what we're going to do and I think I can switch this video here and move that camera. So let me pause for a moment. Okay, so we want to use these kinds of motors, and these motors basically can move from a range of -90 to +90 degrees. And the way that we do that is we are now going to generate a pulse width modulated signal that has a pulse width of 1 to 2 milliseconds. If I have a position of 1 millisecond, that will move me to the far left, and if it's 1.5, I will be pointed straight ahead and then 2 milliseconds, I'll be roughly 90 degrees to the right. And this signal needs to be provided to the motor every 20 milliseconds. Now, if I'm going to use a sequence of or system with multiple servo motors, so for example, let's say I want to steer all 4 wheels independently, then you'd say, well, we need a number of output compare circuits. And oh, by the way, maybe these output compare circuits aren't perfect for, we need external circuitry to be able to drive motors. So one of the things about motors is motors tend to take a little bit of power. So I'll set this all up on Monday, both with servo and stepper motors, we'll see that we have external power supplies and our devices are configured such that we can power motors using external supplies and using the logic voltages that we need to actually control all the digital circuitry. So this circuit here now is going to basically move from left to right using this signal, and I think I have a sketch already. So if I have my pulse at 1 millisecond, you see the armature is off to the left. If I have it at 1.5 milliseconds, it's straight ahead. And if I move it over to I want to move it to the right, then I change my positioning to my pulse to 2 milliseconds. And so what we want to do is we want to vary this pulse width, very much like what we just did with our output compare. So if we have a number of motors, and for example, the MX4 boards has a connection for 8 different motors. It has a set of pins that you basically connect the motors directly to the board. Well, the MX7, they removed that, and we have an interface module that now will control a couple of motors, and we'll use that on our demos on Monday. But what we have to do is we have to basically provide this control signal. And so we have a different strategy that we're going to use for this signal or this system. First thing we need to do is we need to have a synchronization. We need to provide these signals every 20 milliseconds. So if I think about it, I want to control 8 motors, and let's say that they're all fully to the right. So I need 8 pulses of 2 milliseconds, so that's 16 milliseconds. So I still have a little bit of a leeway, so I could control 8 motors if I could do them in sequence. So if I do motor 1 for the first 2 milliseconds, motor 2 for the next 2, and so on, and I have them all synchronized to this 20 millisecond time, then I can do that. So the strategy we're going to use is, let's see if I have that one. No, I don't have that one up. Let me bring that up. Must be this guy. So what we're going to do in this case is we're going to use our ADC. We'll use our ADC because our ADC is going to tell us what our pulse width is going to be. But what I want to illustrate in today's lecture is how we can use timers to do that. And we'll use the oscilloscope to actually observe that operation. And so what I'm going to do is, because then I power back up, that's not going to. Okay, so I'm going to use a timer. I'm going to use timer 1 that's going to generate a 20 millisecond interval. And so what I have to do is I have to configure timer 1 so it has a period of 20 milliseconds. So first thing I have to do is I have to calculate what is going to be the count that it will take to do 20 milliseconds. So I say, all right, if I divide my input frequency by 8, so I have a 10 megahertz and I have a 1 1/8 of a megahertz. So if I do that, I calculate that my period is going to be 61A8. That's the hexadecimal value that will be in the period register that will cause it to generate an interrupt every 20 milliseconds. And so if I want to change my scaling, and the reason I use the 8 is I want to make this as fine of resolution as I can. Recall timer 1 only has a limited number of prescale options. And so I'm going to use that to generate my interrupt. And let me load this project. let's run. Okay. So now what I see is that, and I'm not so much interested in the pulse width right now. What I'm interested in is the period. And so notice what I'm doing is I'm generating a pulse every 20 milliseconds. Now notice my pulse here is a little bit large. It's kind of maybe, well, let's see what it is. Get over to 0 here. So if I measure it very carefully, I see that it's about 2.5 milliseconds. So let's bring that down. If I can get this engaged in the... So this would be roughly the maximum that we would use to drive our motor. Okay, so now we want to do is we say, all right, we want to, I need 5. I want to verify that my period is actually 20 milliseconds. And it looks like it's right on. And so we say, all right, I could actually generate pulses for 8 motors. So I could do the pulse for motor number 1, and then I could start the pulse for motor number 2 using exactly the same timer. And so in a round robin fashion, I can now, using timers, generate outputs to be able to control these various motors. And you see that I can control it from, well, essentially 0, but the motor is going to want a signal from 1 millisecond to 2 milliseconds. And so that's where we again come back to our, we're going to generate this kind of signal so that we can control the position of those servo motors. So again, the servo motor has a limited range of motion. It goes from minus 90 to plus 90 degrees relative to the housing. Now, if we look at these motors, if we look at the torque, we see that it's actually going to be fairly light. I mean, it's not going to be turning a car kind of linkage for steering, but for small robots, this would be very, very appropriate. Now, these motors are actually very inexpensive. I think they're like on the order of $5, so you know it's not going to be anything very high quality. But, and when we actually start driving them, we'll see that there's a little bit of jitter in some of these motors, and depending on the voltage that we apply and so on. So that's another advantage of using external power, is these motors are rated, I believe it's 5 to 6 volts, and so if we're running them from the voltage, so 4.8 to 6 volts, and when we run them directly from the board, we find that the supply voltage is a little too low, and so they're not very precise in their positioning. Okay, so what we're doing is we're generating output compare or pulse width modulated signals using timers instead of the output compare. Could we use the output compare instead of the timers? We could. The only thing we need is we just need to ensure that we connect those outputs to the appropriate driver circuitry so that we provide the appropriate power inputs to the motors so that we can drive them. However, if we use the output compare, we see that when we looked at our board, come back to this here, we see that we have 5 output compare. The other thing is when we start using this, we also need to consider where are those signals available. So notice here, output compare and port D pin number 1 are shared. Same thing, port D pin number 2 and output compare. So we see those are shared. And in fact, I'm using this port as my timer output, so I don't have to change my scope, so I can give you the demonstration. But if I wanted to use both of those, I would have to make a decision which one am I going to use, because I can't use them both simultaneously. So this is why I'm changing demos, because I have to use one or the other, which is the reality of when we use these microcontrollers. Now, unfortunately, we don't have enough time this semester, given that we had a couple-week delay, and of course you don't have time, you can't come in and actually do the labs. But this is a very, very interesting lab where we actually start controlling motors, and I'm hoping that you're starting to see that we can use these microcontrollers to do a lot of different sorts of applications. As a matter of example, I had 2 students do a honors project where they were actually positioning solar arrays. So you see these systems that have the positioning of the solar array both for elevation and for the azimuth, so they would track the sun, so the sun would be incident orthogonally, would be at a right angle to the plane of the collectors for maximum efficiency. And so they implemented that on one of these microcontrollers. They implemented all the calendar functions of the day of the week. They had the day for sunrise, sunset for the day of the year to know where the sun elevation is as it changes, as the Earth's position relative to the sun changes through the seasons. So they had all of that implemented, and they did that with one of these microcontrollers. So you see that these things are tremendously capable for a lot of different kinds of applications. So what we're going to do next time is we'll actually use some of these motors, and then we'll talk about a different class of motor called the stepper motor. Stepper motor is different from a servo motor in that the stepper motor uses a different sort of excitation of the windings. So on this servo motor, you have a constant bias on the windings, and then you provide a control signal. On the stepper motors, now we're energizing windings in a certain sequence to allow them to be able to move either with coarse or fine positioning. And you can use those for very fine positioning, and we'll talk about some of those applications in the next lecture. Okay, one last thing is there are the quizzes associated with the labs. I tried to get them all out as quickly as we could, and I need you to get those all done by next Friday. So the videos that you see, let's see, there's a question here, is the number of servos we can use intended to the number of timers. Actually, you could use, so in this example here, we're using 2 timers. And if you wanted to, well, you are operating them independently, because what's happening is when you go through that timer loop, you are basically providing a input signal, and you could have separate input signals to do that. And you can operate them independently. You can operate more than 8. You can use, so we have 1 timer for the heartbeat, the 20 millisecond, and all of them will need that. I could use 1 timer for 8 motors. I could use another timer for another 8 motors. I could do 16 motors. I would need to use 3 timers to do that, and those input signals could all be done independently. So yes. Okay, so as I was saying, make sure that you get those lab quizzes done. This is my way of seeing, are you learning the material that we're talking about in the labs, and this is how we're going to do the equivalency of you actually doing the labs. We have to have something. Remember, this is a 4-hour course, so this is going to be the little extra work that you need to do in the course as well. So next time we'll actually get involved with driving motors. We'll show you some of the instance or some of the details of having to do that, and then we will wrap it up on next Thursday. And for the final, what I'll do is I'm going to actually post the final right after class next Thursday, and you will have until the following Wednesday to submit it. So if there's any other questions, let me know. Otherwise, I'm going to stop the recording. Let me stop the oscilloscope. Let me stop this. And let me stop the recording.
Recording stopped.